Hey everybody, this is Mrs. Harding. Today what we're going to talk about is activity 9.1c. Up to this point we've been talking about confidence intervals. We started in chapter 9 with hypothesis testing. We've talked about the alpha level to interpret the results and make a decision about your hypothesis test. And so what we're going to cover in this video is the errors that can happen related to your hypothesis testing. Now there's two different errors that could happen. Is it possible that we could reject a null hypothesis even though it's true? Yep, that's a possibility. Is it possible that we could fail to reject a null hypothesis that's actually false? That is true also. So these are the two types of errors that we're going to investigate. And we're also going to talk about something called the power of the test. Now take a look at the first example there with potatoes. It says a potato chip manufacturer needs to decide whether or not to accept or reject an entire truckload of potatoes by sampling an SRS of potatoes from the truck. In business, this process is called acceptance sampling. The company will reject a load of potatoes if more than 8% of the potatoes have blemishes. Stop the video and take a minute and write down what you believe the null and alternate hypotheses are. Go ahead and check what you wrote down with what you see on the screen. The null hypothesis is that the proportion of blemished potatoes is 0.08, so no more than 8% of all potatoes have blemishes. And the alternate hypothesis is that this proportion is actually greater than 0.08. So the assumption really is that the potatoes are okay unless we prove otherwise. Now, sometimes at this point, students will ask, why is the null hypothesis not less than or equal to 0.8? Well, we're choosing 0.8 because that's the largest possible proportion that would still be acceptable. And we need a definite number for determining our mean and standard deviation for the sampling distribution. So we take the largest number to come up with the most conservative sampling distribution. So then underneath this, it says, based on the p-value and the alpha level, we will either reject or not reject. So what does it look like in those two examples of errors rejecting a true null hypothesis? What would that mean in this case? Well, in this case, that would mean that we would actually decide that the proportion of blemished potatoes is greater than 0.8 when really it's not. So we would be rejecting the null hypothesis even though it's true. The other error, failing to reject a false null hypothesis. So we would say that we don't have evidence to reject it when in fact the proportion of blemished potatoes really is greater than 0.8. Turn to the next page. If we're going to add some context to this, it says in the potato problem, we might incorrectly reject a good batch or fail to reject a bad batch. So rejecting a good batch could cost the company and their supplier money, while accepting a bad batch may cause problems with the consumers. The context for these types of errors is important to understand too. Sometimes the consequences of the errors are about equal. Sometimes the consequence of one error versus the other is actually much more severe. So let's actually define these two types of errors. They're called a type 1 error and a type 2 error. The type 1 error is rejecting the null hypothesis when it is actually true. And you can see in the chart there, it shows you these errors. It has whether or not the null hypothesis is true or false, and whether we have decided to reject or fail to reject. So if we reject the null hypothesis when it's actually true, that is a type 1 error. If we fail to reject it and it's false, that is a type 2 error. Now remember, all of our decisions are generally made about one sample. So it's always possible to get a sample that leads you in the wrong direction. We're going to take a look at a couple of other scenarios that we could apply a type 1 and type 2 error. And we're going to talk about what these errors actually mean in context. You can see in number 3, it says in medical disease testing, the null hypothesis is the assumption that the person is healthy, and the alternative is that the person has the disease we're testing for. In a test for a particular disease, a positive test indicates that the person might have the disease, and a negative test indicates the person likely does not. Pretty relevant now. You've probably heard a lot about false positives and false negatives with COVID testing. So in part A, what would be considered a type 1 error in a medical test for a disease? This is referred to as a false positive. Well, a type 1 is rejecting the null hypothesis, even though it's true. So if the null hypothesis is the person is healthy, then we would be deciding that the person has the disease when they really don't. So we would reject the idea that they're healthy. We'd say they have the disease, but actually they are healthy. How about a type 2 error? What would that be? Sometimes called a false negative. So a type 2 error is failing to reject the null hypothesis, which says the person is healthy, even though it is false. So we would actually decide that the person does not have the disease when they really do. Which one of those do you think is more serious? A second example that we can talk about, I'll just show all of it to you on the screen here, is in the criminal justice system. The idea is that a person is presumed to be innocent until proven otherwise. So in other words, the null hypothesis is that the defendant is innocent. The alternate hypothesis is that the person is guilty. So what would a type 1 and a type 2 error mean in this case? A type 1 error is rejecting the null hypothesis even though it's true. That would be like convicting an innocent person. We reject their innocence. We decide they're guilty even though they really are innocent. What would a type 2 error be? A type 2 error is failing to reject when it is false. So this would be saying, oh, the person is innocent even though they are actually guilty, or freeing a guilty person. Which one of those do you think is more serious? Go ahead and flip to the next page. What we're going to talk about is the probabilities of making a type 1 error, a type 2 error, and then the power of the test as well. Obviously, we don't want to make any mistakes when we're doing hypothesis testing. But because we are drawing a conclusion at the end, we're either failing to reject the null hypothesis or we're rejecting the null hypothesis, there is always the possibility of making one of those types of errors. So what we're going to take a look at here is the probabilities. And in the paragraph at the top, it says, note that the probability of a type 1 error is the conditional probability that we reject the null hypothesis given that the null hypothesis is true. And I point this out because we're going to be examining a sampling distribution in which the null hypothesis is true to talk about that. And then in the next sentence, the probability of the type 2 error is the conditional probability of failing to reject the null hypothesis given the null hypothesis is false. So given that the null hypothesis is false, we're going to be examining a different sampling distribution. Clearly, we want to make the probabilities of coming up with these errors as small as possible. Potentially, there might be one error that's more serious, and we're more focused on minimizing the probability of making that error. Is it possible to make a type 1 and a type 2? It is not possible to make both at the same time because they are both dependent on different conditions. In one condition, it's dependent on the null hypothesis being true. The other, it's dependent on the alternate hypothesis being true. So if we come back to this example of the potatoes, I'm going to kind of walk you through all the things that are on the screen right now. Says, suppose the potato chip company decides to carry out this test based on a random sample of 500 potatoes, n equals 500, using an alpha level of 0.05. All right, so here on the screen, we've got a lot of information there. It says, consider the sampling distribution of p hat below. Determine the mean and standard deviation. Okay, well, the mean will be 0.08. Standard deviation determined here to be 0.0121. Says then determine the value of p hat that would result in rejecting the null hypothesis at the alpha level of 0.05. All right, the alpha level of 0.05, that would be up here. The most extreme upper 5% of possible samples is the area in which we would end up rejecting the potatoes. So the question is asking you to find the p hat value that would lead you to this cutoff point right here. Clearly the answer is there on the screen, but I'm going to show you exactly how we got that. So first of all, I need to know what the critical value is for this point. You're going to do an inverse normal of 0.95 to get a critical value of 1.64. All right, so we're going to go back to what we know about confidence intervals. This right here is the upper limit of the confidence interval of a 90% confidence interval. This is the upper limit. So we're going to go 0.08 plus 1.64 times the standard deviation to get this 0.10. So right here, if we ended up with a sample of potatoes in which 10% of them are blemished, we would decide that that is significant at the alpha level of 0.05, and we would end up rejecting those potatoes. So what you're looking at on the screen is anything to the left of this blue line would be a sample then where we would fail to reject that the potatoes were bad. We would fail to reject the null hypothesis. Any of these samples on the sampling distribution would be considered so rare that if we got them, we would actually reject the null hypothesis and we would say that it was a bad batch of potatoes. Okay, go ahead and flip to the next page. If you're looking at the answer key, it's probably not completely clear to you what all the shading is. So I'm going to start with a blank copy here to kind of help you understand what all these different regions are in here. So it says, remember that the probability of a type 1 error is a conditional probability of rejecting the null hypothesis given the null hypothesis is true. What area in the above distribution represents this probability? Okay, we're not necessarily going to talk here yet about that blue one, but here where the mean is 0.08, this blue line, this is the same blue line from the previous diagram, represents the place in which that we would reject, so p hat being 0.10. This area right here in the diagram that you're looking at would be the area, those would be the samples that would cause you to reject the null hypothesis. So the area to the right of p hat equals 0.1 under the normal curve to the left. That is where the type 1 errors occur. All right. In this next section, I'll go kind of slow so you can see what I'm all shading in there. But it says the probability of the type 1 error is easy to find. It's simply the alpha level of the test. Okay? So if you go back here, remember this area that I shaded represents 5%. That's the top 5% in the sampling distribution. So there's a 5% chance of making a type 1 error. And this will be true in any sampling distribution. Whatever your alpha level is the probability of making a type 1 error. The type 2 error is a little more involved. It says the symbol for a type 2 error is beta. The test of significance makes a type 2 error when it fails to reject a false null hypothesis. Sorry, I'm having a little trouble reading. So remember that the probability of the type 2 error is the conditional probability of rejecting the null hypothesis given that the null is false. If the null is false, then the alternative value for the population parameter is true, but what is that value? So what you're going to learn here is that to actually evaluate a type 2 error, you need a specific value for the alternate hypothesis. And that's because we're going to take a look at, remember what it said about a conditional probability? For a type 2 error, we need to go off of the assumption that the null hypothesis is actually wrong and the sampling distribution is actually different. So when it comes to evaluating the type 2 error, we need to look specifically at this alternate hypothesis and the sampling distribution associated with it. Okay, so for the purpose of our example here, number 6, it says, suppose that the null hypothesis is false in our potato problem and that the proportion P of blemished potatoes is actually 11%. Therefore, 11% is the value that we're going to use to calculate beta, or the probability of making a type 2 error. So for just a minute, I'm going to go back up here. Let's figure out which area of this I should label with beta as the type 2 error. So remember, again, this is a conditional probability. So this is saying what's the probability of failing to reject the null hypothesis, even though it's true, given that there is actually some other value for the true proportion of blemished potatoes. Well, that conditional probability means we're looking at the second distribution. So looking at the distribution outlined in blue right here, what's the probability, or where in here would we fail to reject? We would fail to reject over here. So this probability right here that I'm drawing squigglies into is beta. The area right there represents the probability of making a type 2 error. All right, now that we've identified which area on the diagram represents the type 2 error, I'm going to talk you through these calculations for actually figuring out the value of beta. So beta is the probability that p hat is less than 10. Remember, that was to the left of the rejection line because we're failing to reject. Given that p is actually equal to 0.11. So that means, given that we're looking at that second distribution that was outlined in blue, where the mean was 0.11. So what's the probability of getting something less than 0.10 given that the mean is 0.11? We're going to need to figure out the standard error. So you can take a look there, the standard error of the normal distribution to the right. And then we have to determine our z value, our z-score, for a proportion of 0.10. And then we're going to go through and determine the probability of that z-score. There's about a 23.74% chance of getting a value less than 0.10, given that the true mean is 0.11. So the value of beta is 0.2374. That is the probability of making a type 2 error. What does that mean in the context of the problem? So interpreting it in context, the probability of not rejecting the null hypothesis when it is actually false. So in other words, the probability of accepting a bad batch of potatoes. So it is actually false, but we failed to reject it. It's a bad set of potatoes and we failed to send it back. That would be the type 2 error in this context. Okay, if you flip to the next page, this is where we're going to start talking about something called the power of the test. And part D says label the unshaded area in the sampling distribution on the right as 1 minus beta. It is the complement of a type 2 error. What's the value of this area in the example? How do you interpret this area in context? Okay, so let's flip back to the diagram that I was filling in for you. Okay, so take a look at that. We had the type 1 error here, which was given that the null hypothesis was true. We're talking about now, given that the null hypothesis is false, this beta, the squiggly blue area that I colored in right here, that is the probability of making a type 2 error. So the complement of that, let me get, how about a little yellow highlighter, is over here. The rest of this sampling distribution is 1 minus, probably shouldn't have done that with a highlighter, but hopefully you can see that, is 1 minus beta. So that is the complement of beta. Okay, back to then the question that we were looking at. Label the unshaded area in the distribution on the right, 1 minus b. That's what we just did. It is the complement of a type 2 error. What's the value of this area? It's just 1 minus beta, so 1 minus 0.2374. That gives you 0.7626. So what does this actually represent? So this right here, we have rejected it given that it's false. That's the area of the distribution where we would be rejecting it, and it was false. So this is the probability of rejecting a false null hypothesis. In our example, this is the probability of correctly rejecting a bad load of potatoes. This is the area of the distribution that is going to allow us to correctly reject a false null hypothesis. And you can see in the next question, the probability of rejecting a false null hypothesis is called power. What's the relationship between power and beta? They are complements of each other. 1 minus the power is what beta is. 1 minus beta is the power. The power is the complement. How are the power and alpha levels related? So we're thinking about as one increases, what happens to the other? Well, let's go back up and take a look at the diagram. I'm going to look at the diagram that's in the answer key that you see, not the one that I just filled in. So let's think about what all this stuff is right here. This red area is a type 1 error. The green area, beta, is type 2 area. The black here, 1 minus beta, that is the power of the test. So if you think about moving this line around, as alpha increases, so that means that our alpha level is getting bigger. This line is actually moving to the left. You're making more area there in alpha. What happens to a type 2? It gets smaller. What happens to the power? The power gets larger. So as alpha increases, beta decreases, and the power increases. What if we decrease alpha? If we decrease alpha, that's taking this rejection line right here and moving it to the right. That makes beta larger, and it makes the power smaller. So I'm going to go back to that question again, and you can read through it. As alpha increases, beta decreases, and the power increases. As alpha decreases, beta increases, and the power decreases. Alpha and power are generally doing the same thing. Beta is doing the opposite. Okay, go ahead and turn to the very last page. Question number 7, or problem 7. When we calculate power, we are calculating the sensitivity that the test can correctly reject a false null hypothesis against some alternative. So specifically in the case that we were talking about, we found the power to be 76% when the alternate was 11%. You can see that that probability is based on the exact value that we chose or we knew for the alternate hypothesis. Thus, the probability that the company can correctly detect and reject shipments where 11% of the potatoes are blemished is 0.76. So if the shipment contained 10% blemished potatoes, would that increase or decrease the power of the test? And why do you think so? So obviously you can see from the screen that it will decrease it, but why exactly does that happen? I'm going to scroll back to the diagram again. I'm going to keep coming back to this diagram. If our alternate hypothesis is actually 11%, we have taken this entire alternate sampling distribution in blue and it is shifted to the left. It's actually increasing the probability of making a type 2 error. This rejection line doesn't change. That rejection line is there at the 0.05 level. But because we would be changing the mean of this distribution to the left, we'd be taking it from 11 to 10, it would actually decrease this area that represents the power of the test. It would actually be more difficult to accurately detect a bad load of potatoes. Okay, if we head back to the last page there, the last piece that we're going to talk about here, you might be thinking, is 0.76, a power of 0.76, is that strong? Is that not strong? How does that relate? And it says in the top there, it depends on how important it is for you to be able to detect a false null hypothesis. It depends on how serious you think each of your errors might be. The power of the test, because it's a probability, ranges from 0 to 1. What does a 0 mean? It means that your test will never detect a false null hypothesis. What does a power of 1 mean? It means that your test is guaranteed to pick up on a false null hypothesis. So if we're going to interpret the power in those other two examples that we had the example of medical testing and we had the example of the criminal justice system. So interpret power in the context of the problem given in the medical testing. This is the probability of correctly detecting a disease. Seems fairly important, right? The power of the test is how likely is it to pick up on the fact that someone does have a disease and they're not healthy. How about the power in the context of the criminal justice system? Oops, sorry about that. This is the probability of correctly convicting a guilty person. So we need to correctly pick up on the fact that the null hypothesis is false, the person is not innocent. All right, this has been a pretty heavy topic, a pretty in-depth activity. So please, whatever questions you have, let Mr. Bowman or I know. Enjoy the rest of your day.